In class today, we're going to start talking about compressors. And compressors are devices that are used in chemical processes that raise the pressure of a gas. And that can be done to facilitate a reaction at high pressure. It could be done to induce flow. And essentially the operating principles for a compressor are that you flow in at some lower pressure and lower temperature, and then your gas leaves at a higher pressure and a higher temperature. And to do that, work is done, okay? So we know that we're gonna have some shaft work here. And to help us figure out maybe how much work needs to be done, we probably should start with our energy balance. So dNU dt is Q plus W plus the sum of the enthalpy that's entering the system from flow minus the sum of the enthalpy that's leaving from flow plus the velocity terms plus the change in gravity. Okay. Now, there are several assumptions that we can make for an operating compressor. The first one, of course, is that we're going to operate this thing at steady state. Another very common assumption is that it's adiabatic or well insulated, that the change in the height is not significant, and that's pretty accurate, and that the gas velocity in and the gas velocity out are approximately the same. So our energy balance simplifies to 0 equals the work plus the sum of the enthalpy in from mass flow minus the enthalpy that's leaving from mass flow. And through this compressor, the composition isn't going to change. So M in is equal to M out. And so what happens then if we have one component, like steam would be pretty common, or some other gas like oxygen or air, that our energy balance simplifies that the work is just equal to the mass flow rate times the change in the enthalpy. Okay. Now, there are other assumptions that we might be able to make for an operating compressor as well, like, is it reversible or not? And that's going to tell us something about efficiency. And so in class today, we're going to start talking about entropy and efficiency and talking about how those are linked to one another and using a compressor as sort of the vehicle to do that. All right, so we'll solve two problems. Well, really, I guess it's one problem for a compressor just in two different ways. And then we'll start talking about efficiency a little bit after that. So let's look at our problems that we're going to solve today, okay? So the first one asks us to calculate the amount of work that's required to reversibly compress oxygen from atmospheric pressure and 25 degrees C to 150 atmospheres. All right. And so if we think a little bit about this, why this word reversible is important actually doesn't just lie in the entropy balance, but also in the energy balance. Because we know to calculate the enthalpy, we're going to need to know what the final temperature is. And that's not given. And that's where this information that we have about whether it's reversible or whether we would, as in the last example problem we'll do today, have an efficiency is really going to come into play. So we're going to have to somehow use our entropy balance to determine what the final temperature is going to be. Now, our open system entropy balance, you're actually asked in your homework to prove that for a reversible adiabatic system, that, of course, the reversible means that Sg is equal to 0. But the combination of these two is that the change in the entropy of the system is also equal to 0. And like I said, that's in the homework. So you guys will prove that that's true. Now, for an ideal gas, we actually have an expression for delta S of the system already. And we know that delta S over R is equal to the integral from T1 to T2 of Cp over R dt over T minus the natural log of P2 divided by P1. So for this reversible adiabatic system, delta S over R is equal to 0. And so if that's the case, then we know that the natural log of P2 over P1 then equals this integral from T1 to T2 of Cp over R dt over T, okay? And in the problem statement on the right-hand side of the screen, we're asked to solve this in two different ways. One, assuming, of course, that it's a simple ideal gas, right, which is when the heat capacity is equal to a constant. And second, when we actually take the temperature dependency of the heat capacity into consideration. So let's do the first one, where we have a simple ideal gas, and then we'll solve the second one, where we still have an ideal gas, but it's not simple. We allow the heat capacity to change with temperature, okay? So we know that when oxygen can be considered to be a simple ideal gas, that it's a diatomic molecule. So that just means that Cp is equal to 7/2 times R. And so then this becomes the natural log of P2 over P1 equals the integral from T1 to T2 of 7/2 R over R, which is 7/2 times dt over T, or that the natural log of P2 over P1 equals 7/2 times the natural log of T2 over T1. And of course, we're after T2 in this particular problem. So let's just do a little bit of simplification, that the natural log of P2 over P1 is the natural log of then T2 over T1 to the 7/2. Then we get that P2 over P1 is equal to T2 over T1 to the 7/2. Or finally, that T2 is equal to T1 times P2 over P1 to the 2/7. And in this problem, we know that T1 is 25 degrees C, so that's 298.15 Kelvin. We know that the final pressure is 150 atmospheres, and the initial pressure was 1 atmosphere to the 2/7, right? So that gives us a final temperature of 1248 Kelvin, or if you prefer, 975 degrees C, okay? So now we have our final temperature, and we use this, or we obtain this from the entropy balance. And this is something that you're going to have to keep in mind as we move forward through the semester. Every single time that we solve a compressor problem or a turbine problem, which will be the next sort of collection that we talk about, you will always solve the isentropic case when delta S is equal to 0, every time, because the isentropic case is the thing that sets when the efficiency is equal to 100%. And you'll see why that is important maybe in the third part of this lecture. So, all right, so we found essentially what the isentropic final temperature would be, right, when we have a reversible system. And so now that we have the final temperature, of course, we can answer this question because we know that the amount of work is m dot delta H. And so if we have the second temperature, we now know, of course, that delta H is equal to the integral from T1 to T2 of Cp dt. And so we know then that our heat capacity is equal to 7/2 times R. So that gives us 7/2 times R times T2 minus T1. So that's 7 halves times 8.314 joules per mole Kelvin times 1248 Kelvin minus 298 Kelvin, right? So delta H then is equal to 27,600 joules per mole, or if you prefer, 27.6 kilojoules per mole. Okay. All right. How was this? Do you guys have any questions?
I think it was pretty similar to your the problem last lecture, so I think I can understand.
Yeah, it is pretty similar. We are repeating that a little bit. I did notice, like I said in the messages I sent, not everybody's actually watched the last lecture, which was asynchronous. So I do encourage everybody to do that. Okay, so if this makes sense to you guys, right? We calculated the final temperature and delta H from the case where delta S was equal to 0, and we had a simple ideal gas. So what is going to change in this problem if we assume, if we don't assume that it's a simple ideal gas? If we actually consider that the heat capacity changes with temperature? Anybody? What would actually be different?
Well, I mean, your heat capacity is probably going to be greater, I would guess, but I don't know how that would really affect the outcome.
Would anything in the methodology change? So would any of these other, would this equation change, for example?
Only the integral.
Yeah, only this. So that's something to keep in mind, is that everything that we've done in this problem so far, where we know that for a compressor that the work for an adiabatic compressor is equal to m dot delta H, the fact that for a reversible adiabatic system that delta S is equal to 0, and that would mean that for an ideal gas, even if it's not a simple ideal gas, that equation still holds. And so the only thing that really changes if we allow the heat capacity to change with temperature is really just that integral. And more specifically, it's really just that term, okay? So let's solve the problem and then compare our values for the final temperature and delta H when we allow the heat capacity to change with temperature, okay? So we will start doing that at the exact same place, right? Delta S over R is still equal to 0, and that's still equal to the integral from T1 to T2 of Cp over R dt over T minus the natural log of P2 over P1. And so the natural log of P2 over P1 again equals then the integral from T1 to T2 of Cp over R dt over T. So now instead of assuming that Cp over R is equal to 7 halves, now we have a functional form for this that comes from your book, right? That Cp over R equals A plus Bt plus Ct squared plus D divided by T squared. And so let's put that in that equation. So the natural log of P2 over P1 equals the integral from T1 to T2 of A plus Bt plus Ct squared plus D divided by T squared times dt over T. And if we distribute the T in the denominator, then the natural log of P2 over P1 is the integral from T1 to T2 of A over T plus B plus Ct plus D over T cubed dt. And of course, that integral is relatively straightforward, right? So that's P2 over P1 equals A times the natural log of T2 over T1 plus B times T2 minus T1 plus C over 2 times T2 squared minus T1 squared, then minus D over 2 times, and here let me just put that underneath a little bit so I don't run out of room, minus D over 2 times 1 over T2 squared minus 1 over T1 squared. Okay. All right, so what do we do from here?
Get values for A, B, C, and D from the table.
Yep, so if you go in the appendix in the back of your book, right, so then A is 3.639, B is equal to 0.506 times 10 to the minus 3, C is equal to 0, and D is equal to minus 22,700. Okay. And there's only one unknown in this equation, right? And that's T2, right? That appears in every one of these terms. So you could plug this into your calculator, or I just set up a very simple Excel file where I'm going to goal seek, T2 until this equation is satisfied. And when I did that, I found that the final temperature was equal to 1169 Kelvin, which is 896.8 degrees C. Okay. So that's pretty significantly different than what we calculated in the previous problem where the heat capacity was equal to a constant. And maybe that shouldn't be too surprising. Remember, we've looked in our book a couple of times now in chapter 4, where they have a plot of the heat capacity as a function of temperature. And they have, I believe they have nitrogen, not oxygen, but they're very, very similar. And remember, that starts at a value that's around 7/2, and it drifts up, right, with temperature. And so if the heat capacity increases with temperature, this means that as the temperature goes up, it takes more energy to heat it by another degree C. So if that's the case, then the value for the final temperature that we should calculate is lower than it is if you assumed that the heat capacity were a constant, right? And maybe another way to think about it is that, remember that, R times the integral of from T1 to T2 of Cp over R dt is delta H, right? So if we actually looked at this, what's the integral of Cp over R dt? It's just this, right? Right? It's literally taking that plot that they have and finding the area under that curve. So, let's say that was delta H. Well, delta H, may or may not be the same in this problem. We'll figure that out in a minute. But let's say it were approximately the same. Well, if you had the same amount of heat and the heat capacity from one was equal to a constant, well, now we get to go all the way up here, but we have to make those areas equal to each other. And the only way to really do that would be like this, right? So the area of these two shapes that I've drawn are approximately the same. But obviously, when we let the heat capacity go up, that the final temperature is lower, okay? So we did calculate this temperature. So let's see if this idea about delta H being the same is true. So again, right, that the work is equal to m dot delta H, right? We calculated delta H in joules per mole, so maybe we'll make that little w is equal to delta H, which is just the integral, like I said above, right, which is just R times the integral from T1 to T2 of Cp over R dt, right? And this, again, is A plus BT plus CT squared plus D divided by T squared. And we've taken that integral a couple of times now, right? That's just equal to A times, or here, maybe this is a little bit better. That has to be R, which is 8.314, times A times T2 minus T1 plus B over 2 times T2 squared minus T1 squared plus C over 3 times T3 cubed, or sorry, T2 cubed, there is no T3, minus T1 cubed, minus D times 1 over T2 minus 1 over T1. And if you do that calculation, you'll find that the work is 27.9 kilojoules, or 27,900 joules per mole, kilojoules per mole. So that's pretty similar, right? And so when we started to talk about the heat capacity changing with temperature, and we were trying to figure out whether you should take the change in the heat capacity into consideration, right? We had examples where it was a really good idea or really important to do that, and other calculations where we were less sure. And this is one of those cases where, for a fluid like this, where that line is straight, this is always going to be true, that the work that you'll calculate is going to be approximately the same. The time that you really have to worry about this is if it has curvature to it. And okay, that's one side of this, is the work side. The other one is the temperature side. So we have an 80-degree difference between the case where the heat capacity was allowed to change and where it wasn't. And whether or not maybe that temperature difference is important depends on what it is that you're doing in your reacting system. So let's say we wanted to preheat the gas to enable a reaction at 900 degrees C. Well, in one case, we're way over, right? 975, we might have to remove heat. In another one, we get it spot on. And of course, that also depends on delta H of reaction and all that kind of stuff. After you do this compression, you might also want to keep the pressure relatively high, but then extract some heat for some secondary process and do heat recovery. So if that's the case, then also the temperature that you're looking for is going to matter. So, you know, there's no clean answer here whether it matters which way that you do it or not, but it does certainly depend on what variable it is that you're looking for. If you're looking to design the compressor for oxygen, no big deal. You'd buy the same compressor no matter what calculation you did. But if you're really interested in the temperature and heat transfer, obviously something's going to have to be accounted for, right? Or the change of temperature should be accounted for. Okay. All right. Before we move on, does that make sense to everybody?
Makes sense to me.
All right. Anybody else? Questions, comments? No? Okay. So then let's ask a slightly different question. So how much work would be required if the compressor efficiency was 80%? And then if the compressor is not operating at 100% efficiency, it's at least implied that entropy is going to be generated. Okay. So let's think about this a little bit. What would happen if our efficiency is less than 100%? And how that's going to influence the calculations that we do. So when the efficiency of a compressor is less than 100%, what does that actually mean? For the amount.
I think it would mean that I guess, the proportion of work to waste heat would be smaller. So like if work was in the numerator, it would be smaller, and then the denominator would grow if it's waste
Yeah.
heat.
Yeah, so one way to think about it too then is that, well, if we're operating at 100% efficiency and it's reversible, how much waste heat are we generating?
Zero.
Yeah, none. Absolutely. That's correct. So if we have an adiabatic, perfectly reversible compressor, we're not generating any waste heat at all. And that's the thing that allows the efficiency to be 100%. It's like everything that you're doing to the gas, or all the work, is going towards the compression, not to generate heat. And remember that just because the temperature goes up does not mean that you're adding or removing heat, right? Because you can still have an adiabatic system where the temperature goes up. So, try if you can not to conflate heat and temperature. Maybe the way that you normally would think about it, it does that, but try if you can not to do that. So at 100% efficiency, yes, the temperature goes up, but there's no waste heat that's generated, okay? So now if we start to reduce the efficiency below 100%, just like you guys just said, now some of the energy that you put into it has to go towards the work, right? You're still doing the compression. And then some of it is lost as heat, right? Or we'll just call it other inefficiencies, but heat is, it's like all drains lead to the ocean, right? It's that all inefficiencies become heat at the end. So if that's true, then what that means is that when the efficiency is less than 100%, we still need to do that amount of work to do the compression that we want to do. But the work that we've done is actually greater than the shaft work that we did when we were reversible, okay? And if that's the case, right, that also means that delta H is going to be greater than when the work was isentropic, okay?
Are you
So
saying that?
go ahead.
I have a quick question. So WS real, the comparison between those two is just the work required to get the same result. Is that what you're saying? Would
Exactly.
be greater? Okay, gotcha.
Exactly. And maybe this would make a little bit more sense if I wrote it mathematically, that the efficiency then for a compressor, we can define as the minimum amount of work that you could possibly do, which is the shaft work when the efficiency is equal to 100%, right? That's like the isentropic work, divided by the shaft work that we really have to do. Does that make a little more sense to write it that way?
Yeah.
All right, good. Now, just writing this equation, we can already solve that first part of this question on the right-hand side. So in our previous example, how much work would be required if the compressor efficiency is 80%? Well, that's actually relatively straightforward. We could say, well, then the shaft work, right, in the real case that we would have to do is equal to the isentropic case, right, or the reversible adiabatic case, divided by the efficiency of the compressor. So if we just take the result from, let's say, our constant heat capacity case, although they were approximately the same, that was 27.6 kilojoules per mole divided by now 0.8. And so the real work that we need to do is equal to 34.5 kilojoules per mole. All right, so that answers the first part of that problem, which, is relatively straightforward, okay? But the second part of this problem about understanding how much entropy is generated is slightly more complicated. And so let's do that and see if we can make a little bit of sense out of this. So to do that, I want to start with this equation, okay? And I'm just going to rewrite it. And instead of saying that we're considering the shaft work, we're going to consider delta H of reaction. So I could just as easily say from the energy balance then that the efficiency for the compressor is equal to delta H for the isentropic case divided by delta H in the real case, right? And if that's true, well, I'll just multiply delta H real to both sides of this equation. And I find that the efficiency times delta H real is equal to delta H when delta S is equal to 0. And we know that delta H, and again, we'll just assume for this one, so the math is a little bit easier, that the heat capacity is equal to a constant, but it doesn't have to be. So this is the integral of from T1 to T2 of R times Cp over R, or actually, you know what, forget that for a second. We'll just write Cp dt equals, and this one is T2 real, and then that equals the integral from T1 to T2 when delta S equals 0 of Cp dt. And that becomes the efficiency of the compressor times the heat capacity, right, which we are assuming is going to be equal to a constant. And I won't put 7 halves R here quite yet, times T2 real minus T1 equals the heat capacity times T2 when delta S was equal to 0 minus T1. And if the heat capacity is equal to a constant like it is here, the reason not to go up and put 7 halves R is because of those don't go to 0, but those go away. And so we actually can calculate T2 real. And if you just rearrange this equation, you find that T2 real equals T1 plus T2 when delta S is equal to 0 minus T1 divided by our compressor efficiency. And of course, when the compressor efficiency is equal to 1, then T2 real just becomes equal to T2 when delta S is equal to 0. And if we do that in this case, right, we can find then, of course, that T2 real then equals 298.15 Kelvin plus 1248 minus 298.15 divided by 0.8. And that gives us that the second temperature in the real case is equal to 1485 Kelvin, or 1212 degrees C, which is of course a lot more or a lot higher than it was in the initial case, right, where it was 1248. So it's about 200 Kelvin warmer, 200 degrees C hotter. And this makes sense because remember, we have to let off heat, right, as this efficiency. But we're operating an adiabatic, or we have to generate heat internally. But remember, our compressor is still adiabatic. So that extra energy that we had to put in for these inefficiencies, it doesn't escape. It stays inside the system and it heats up the gas, which in this case is oxygen. Okay. Before we actually solve this, one of the things that hopefully you're seeing here is that every time in the future that we're going to talk about efficiency, every time we have to solve the isentropic case, right? We're going to want to know what the we're either going to want to calculate the efficiency given some parameters, right? And in that case, we basically would solve for delta H and then find the efficiency. Or what you would do is be asked what the final condition of the fluid is, and then you'd be given the efficiency and have to calculate the isentropic case. But every time for compressors and turbines as well, we are going to find the isentropic case. So we'll end up finding delta H when delta S is equal to 0, because that gives you the minimum amount of work you could ever do. And we will end up essentially every time also solving that equation where delta S is equal to 0, right? So just keep that in mind. Every time that we're going to do a compressor or turbine problem moving forward, we will solve for the isentropic case. And then depending on what the problem asks, right, we'll either calculate the efficiency, we'll find the final temperature, we'll do other stuff. But like I said, every time we'll do the isentropic case. So now we have the final temperature of the real system, right? So let's try to figure out how much entropy is going to be generated. So to do that, let's look at the open system entropy balance, okay, and how that's going to simplify. So we have that the generated entropy equals, right, dNs dt plus the sum of S out m dot out minus the sum of S in m dot in minus the sum of Q over T surroundings, right? Well, we already know in this problem that we're going to operate at steady state, and we also know that this is adiabatic. And that gives us very simply that the generated entropy just equals m dot delta S, right? Or in this particular case, right, we'll go for the intrinsic case, which is just that, you know, lowercase sg is equal to the change in the entropy. And to find that, we're going to use the same equation that we were using above, except now it's not equal to 0. So we know that delta S over R equals the integral from T1 to T2 of Cp over R dt over T minus the natural log of P2 divided by P1. And so we've done this already where the heat capacity for oxygen is 7/2 R, right? If we're going to continue to assume that this is constant, so delta S over R equals then just 7/2 times the natural log of T2 over T1 minus the natural log, and of course this is T2 real, minus the natural log of P2 over P1. So delta S then equals R times the natural log of 14, well, here I'll write it like this, then we'll put the numbers in a second. T2 real over T1 times 7/2 minus the natural log of P2 over P1. So then delta S equals 8.314 joules per mole Kelvin times 7/2 times the natural log of 1485 Kelvin over 298.15 Kelvin minus the natural log of 150 atmosphere over 1 atmosphere. And so then delta S equals 5.1 joules per mole Kelvin. Okay. And of course, that equals the generated entropy, which is greater than or equal to 0. So that means we didn't break any laws, right? So this process is completely consistent with the second law, which you would assume, right? Because we know it's possible to compress a gas at 80% efficiency. Now, if you were to do something weird, you could say, well, how much work would be needed if the compressor efficiency was 120%, right? Obviously, that's not possible. But you could actually be given problems where you're told, let's say, the final temperature is less than it should be. And you actually could calculate that either the generated entropy was negative or that the efficiency was greater than 100%. And of course, you would know, or at least you should know, that that's not true.